In today's video, we're going to start out with 3 quizkins that review what we learned in the last video. And then we're going to talk about a way to figure out if a reaction is going to be spontaneous or not if the 2 indicators of enthalpy change and entropy change disagree with one another. Let's start with this quizkin here. We're supposed to find delta S for this reaction where tin 4 oxide is reacting with hydrogen gas to produce tin and water. It's possible to find delta S naught by just taking the sum of the standard entropies of the products and subtracting the sum of the standard entropies of reactants. So we'll have to find a table that has those data on it and then use that to make this calculation. So I did a quick internet search and I found this chemistry table. If we look at the headings here, we see that the standard entropy is in this column here, the 4th column over from the left. Well, we're going to need several pieces of data here. One is water vapor's standard entropy, and we can see that that's 188.84. And the unit here is joules per mole Kelvin. We're also going to need hydrogen. And I found that here. Hydrogen gas is 130.7. And again, that's joules per mole Kelvin. We're going to need tin. We have 2 options here, white tin and gray tin. I think I'm going to use the white tin, which is 51.08 joules per mole Kelvin. And we're going to also need tin 4 oxide, which is right below here, and that's 49.04 joules per mole Kelvin. So hopefully you've recorded those somewhere as we look them up. Otherwise, just go to that website. I'll put it back up on the screen here. Stop the video and work out this problem. So my reaction again is SnO2 solid plus 2H2 gas makes solid tin and gaseous water 2 moles. So I know that I'm going to find my delta S naught by taking the sum of the standard entropies of products and subtract the sum of the standard entropies of reactants. So working on the products first of all. For tin, I have 1 mole, and I'm multiplying that by 51.08 joules per mole Kelvin. And then for my water, it's 2 moles, and I'm multiplying that by 188.84 joules per mole Kelvin. That takes care of my products. Now I'm subtracting from that the sum of the standard entropies of my reactants. So for the tin 4 oxide, I have 1 mole, and I'm multiplying that by 49.04 joules per mole Kelvin, plus 2 moles times the standard entropy of hydrogen, which was 130.7 joules per mole per Kelvin. So in the end, I come up with a standard entropy change value of positive 118.3 joules per Kelvin because the moles have canceled out in all of these multiplication operations. Some tables that you'll find will list these in kilojoules per mole Kelvin. Of course, the numbers would be 1,000 times smaller. This next one is asking us for which of the following reactions would we expect to see a positive entropy change. Stop the video and think about them quantitatively if you have to, but try to do it without using numbers, and I'll give you an answer in a bit. Well, the first one is a rusting of iron. If you aren't sure what this process is, it's iron reacting with oxygen. That's what rust is. So it's Fe plus O2. And this is a gas, and this is a solid. And that's going to produce iron 3 oxide, Fe2O3, and that'll be a solid. If we balance this equation, we're going to have to put a 2 here, a 3 in front of the oxygen, and a 4 in front of iron. Now the change in number of moles of gas here is going to be 0 minus 3, so a negative 3. Since the change in number of moles of gas is negative, then we're going to see delta S will also be negative, because remember, more moles of gas means bigger entropy. For the second change, again we can solve this problem with change in number of moles of gas. Delta N gas is, we have 1 mole of gas on the product side coming from 3/2 of a mole of gas on the reactant side, which leaves us a negative 1/2 for our delta N gas. So, therefore, our delta S is also negative. C, compressing a gas. Well, in compressing a gas, we see that the change in volume is going to be negative. You start out with a bigger volume than you end up with. So, for that reason, delta S is also negative because more volume means more entropy. This third question asks, what are the signs of delta H and delta S for a reaction that's always spontaneous? Think about it a little bit and come up with an answer. Well, we know that entropy change being positive favors spontaneity. Also, we know that when delta H is negative, we have an exothermic reaction, and that favors spontaneity. So if delta S is positive for a change and delta H is negative, this thing will always be spontaneous. Next question is asking, what are the signs of delta H and delta S for a reaction that's never spontaneous? Well, increases in stored internal energy, so in other words, a positive delta H, would favor non-spontaneity. And when the reaction gets more ordered, in other words, there's a decrease in entropy, that would also be non-spontaneous. So changes in which the enthalpy is increased while the entropy is decreased will never be spontaneous. So that sets us up for today's discussion. We know that when the signs are opposite, it's either always or never spontaneous. When delta H is positive, delta S is negative, it's never spontaneous. When it's the other way around and delta H is negative and delta S is positive, it's always spontaneous. But what about this? What if delta H is positive and delta S is positive? This says spontaneous. The enthalpy change says non-spontaneous. What's the result? Or, by the same token, we could pose this question. What if we have a decrease in enthalpy as an exothermic reaction? That favors spontaneity. But at the same time, if we have a decrease in entropy, that favors non-spontaneity. So again, we're left wondering which really happens here. Fortunately, there's a tool for solving this problem. The tool for solving this problem was first discovered by this guy here, J. Willard Gibbs, and it's called Gibbs free energy. Gibbs free energy is defined by this equation here called the Gibbs-Helmholtz equation, so apparently he had some help, that says delta G, that's the Gibbs free energy, is equal to delta H, the enthalpy change, minus the absolute temperature times the entropy change for the process. If delta G, once we calculate it, turns out to be negative, that's called an exergonic reaction. Now this comes from X, we always know means out, like exothermic, and erg means work. So this is a work-out reaction. This is a reaction that can produce work. And we're going to come back to that later on in another video and work with that idea that Gibbs free energy is related to how much work a process can do. Exergonic reactions are spontaneous. So another way of thinking about this that might help you remember it is this is free energy for work. So if it can give out energy, in other words, if it's exergonic, it will spontaneously do work. If delta G is a positive number, that's called endergonic. You might have already figured that out because endo means in, and that means it's non-spontaneous. To make this change happen, you will have to provide the work. Work will have to go in, so non-spontaneous. The standard free energy, delta G with the little symbol up there, of course, is delta G at 298 kelvins and 1 atmosphere. So we can define it mathematically as delta G is equal to delta H naught minus T times delta S naught. So let's calculate delta G for the combustion of CH4, given information about enthalpy of formation and entropy that you can look up online or in a reference, or if you have the follow-along notes for this class, they're in the follow-along notes. Well, to get started, we're going to have to give ourselves a balanced chemical equation. So CH4 is reacting with oxygen. Those are both gases. And it's going to produce CO2, obviously a gas. And let's do this for water being a gas because that's what's in our notes table. To balance this, we need a 2 in front of the water and a 2 in front of the oxygen. So delta H is going to be the sum of the enthalpies of formation of products minus that of reactants. So for carbon dioxide, we take 1 mole and we multiply that by negative 393.5 kilojoules per mole, because that's the enthalpy of formation of carbon dioxide. Plus, for water, 2 moles times negative 241.8 kilojoules per mole. That takes care of our products. Now we subtract the reactants. For reactants, we have 1 mole of methane. Its enthalpy of formation is minus 74.8 kilojoules per mole. And we have 2 moles of oxygen, but oxygen has an enthalpy of formation of 0 because it's an element in its standard state. When I sum this all up, I get negative 802.3 kilojoules. So that's my delta H naught. Now we turn to delta S naught, and the process is very similar. We sum up the standard entropies for products and subtract the standard entropies for reactants. So 2 moles, I'm doing water first, times 0.1887 kilojoules per mole Kelvin, plus 1 mole, here's our CO2, times 0.2136 kilojoules per mole Kelvin, minus, now we're at reactants, 1 mole for methane, times 0.1862 kilojoules per mole Kelvin, plus 2 moles times, for oxygen, 0.2050 kilojoules per mole Kelvin. Now the moles cancel out in all of these, and we're left with kilojoules per Kelvin. And the numerical answer is negative 0.0052 kilojoules per Kelvin. So what's delta G naught? Well, delta G naught is defined as delta H naught minus the absolute temperature times delta S naught. So plugging in our information here, delta H was negative 802.3 kilojoules, minus, well, these are standards, so we're at 298 kelvins, times a negative 0.0052 kilojoules per Kelvin. Kelvins are going to cancel in the second term, and we will end up with units of kilojoules, and the answer is negative 800.8 kilojoules. So this is exergonic, and that means this is a spontaneous reaction. Of course, you all know that because you've burned methane in Bunsen burners before. Delta G's of formation are tabulated, just like enthalpy changes of formation are tabulated for various compounds. You can find them in reference books, you can find them on reference tables online. Textbooks also have these things very often. And the rules are still the same. It has to be at standard state. 1 mole of the compound is created from its elements, and those elements have to be in their standard states. And you can use this just like you can in Hess's law to find delta G naught for a reaction. Delta G naught for the reaction is going to be the sum of all the delta G's of formation for products minus the sum of all the Gibbs free energy changes for reactants for the process. Now, to find out what delta G is when you're not at 298 kelvins, you can make use of this fact. Delta H and delta S don't change very much when temperature changes. They do change a little bit, but not very much. So delta H naught is going to be pretty close to delta H at whatever temperature you're at. And delta S naught is also going to be pretty close to delta S at whatever temperature you happen to be at. So you can take delta H naught and delta S naught and substitute those in for the real delta H and delta S in the Gibbs-Helmholtz equation. So delta G at some temperature other than 298, so not standard, will be approximately equal to delta H naught minus the actual temperature times delta S naught. This will be off a little bit, but it'll be a pretty close estimate. So here's an example problem. Calculate delta G for copper reacting with water to make copper oxide and hydrogen gas, and we're going to do this at 227 degrees C. So I'll just recreate my reaction here. Solid copper reacting with water vapor. It's producing solid copper oxide and some hydrogen gas. And the temperature here is 227 degrees C, which is 500 kelvins. So delta G at 500 Ks is going to be pretty close to delta H naught minus T, and by T we mean 500 kelvins, times delta S naught. So let's find out what delta H naught is. I'm going to use values that I've looked up in a reference book. You can find these on your own if you wanted to, but you can trust me here. 1 mole of copper 2 oxide would be multiplied by negative 157.3 kilojoules per mole for its enthalpy of formation. Plus, I have 1 mole of hydrogen, but its enthalpy of formation is 0 because it's an element at the standard state. Minus 1 mole of copper, but that's times 0 because it's an element in its standard state. Plus 1 mole of water vapor, which has an enthalpy of formation of negative 241.8 kilojoules per mole. The moles cancel out, and I will end up with units of kilojoules. The numerical value is positive 84.5 kilojoules. Delta S. Standard entropy change, I can get this also from values that I look up. So 1 mole of copper 2 oxide. Standard entropy for that is 0.0426 kilojoules per mole Kelvin. Plus 1 mole of hydrogen. Standard entropy for hydrogen is 0.1306 kilojoules per mole per Kelvin. That takes care of my products. Now I subtract reactants. I have 1 mole of copper, and that's going to be multiplied by copper's entropy, which is 0.0332 kilojoules per mole Kelvin, plus 1 mole of water vapor, which has a standard entropy of 0.1887 kilojoules per mole per Kelvin. The moles drop out again. My units will now be kilojoules per Kelvin for standard entropy change, and it's negative 0.0487 kilojoules per Kelvin. So delta G at 500 kelvins is going to be equal to the standard entropy change, which is 84.5 kilojoules, minus the temperature, 500 kelvins, times the standard entropy change, which was negative 0.0487 kilojoules per Kelvin. When the kelvins cancel out, I end up with units of kilojoules when I sum these together. I should round it off to the nearest tenths place, and my answer is positive 108.9 kilojoules. So this is an endergonic reaction and is therefore not spontaneous. These calculations can get a little bit tedious, and there's a lot of looking things up in books. Fortunately, you won't have to do a whole lot of these kinds of calculations to become pretty good at it and then able to move on, consider yourself a master. Tomorrow we will wrap up our series on advanced thermodynamics by talking about equilibrium. We've talked about reactions that go forward or don't go forward, like they're spontaneous or not spontaneous, by using Gibbs free energy. But what do we do about reactions that go part way forward and then stop? Well, it turns out that there's a more complicated way to deal with that, but there is a way to deal with it. Learn about it in the next video.